So in this video I'm going to go over electric fields and charges. Now you know that the atom has positive and negative charges. So we're going to apply this idea, though it looks vaguely chemistry based, but we're going to apply this idea to chemistry. You have negative charges due to the electrons on the outside shells, and you have positive charges in the nucleus, in the center, which are found in the proton. Now, we're not going to be looking at the chemical properties of these charges. We're not going to be looking at what happens when you lose negative charges or when you gain them. We're going to be looking at it in a slightly different perspective. Now, considering the electrical properties of a material starts with understanding what kind of material they are in the first place. Now, you have conductors. Conductors are materials that allow negative charges to flow through them, right? So a good example would be metals. And these are the ones that carry electricity. Electricity, at the end of the day, is simply the movement of negative charges from one place to another. And a conductor will allow that to happen. Insulators do not allow the negative charges to move through them. Insulators hold on to their charges. So when you do certain weird and wonderful things to an insulator, what can happen is that it may lose or gain negative charges, but you won't actually get a movement of charges through it. I'll come back to this because it probably doesn't make much sense right now. Now, an example of that would be plastic, glass, and wood. And then we have a third group, which are called the semiconductors, and they're just something we don't even need to worry about right now because they're just plain weird. Silicon, germanium. So let's stick with insulators. These are materials that do not allow the charges to flow through them. Instead, their atoms really hold on to the negative charges. They don't let them go. As a consequence to this, all kinds of weird things happen. You may have had a situation where you felt, for example, your hair stand on end when you took your jumper off, right? What you're suffering from there is static electricity. Another consequence of this is when you get an electric shock, if you scuff your feet a lot and you're wearing rubber shoes and then you touch a metal door, maybe opening a car. What's happening there is that your shoes, rubber shoes, an insulator, are charging you up with that static electricity, and then they make a break for it because the metal is a conductor. Let's see if we can understand all of these weird and wonderful phenomena. Important fact number one then. The relationship between the charges is very, very important. So first, have very clear in your mind that like charges repel each other. They push each other away. So plus and plus repel, as does minus and minus. And then if you have two objects that are charged oppositely, they will attract each other, plus and minus. You would have an opportunity, hopefully, to try this out with some materials in the lab. But basically, if you take an insulating material that is normally neutral, that doesn't initially have a plus or a minus charge, then obviously it will have no effect on each other. But if you do something to these materials which make them either positively or negatively charged, then there will be an overall effect that will depend on that charge. These are acetate rods, so we'll be using these in the lab, or at least you'll get a chance to see them. This would be your hair and a pair of trainers, like the example we've spoken about previously. The effects that we've described depend on the relationship between the overall charge that they have eventually. So how do we get these normally neutral objects to be charged? The main way to charge an object is by friction, actually just rubbing it. So in the case of your hair standing on it, the friction is the jumper rubbing the hair. In the trainer situation, then the rubbing is between the floor and the trainer itself. And when you do your practice in the lab, you'll actually be physically rubbing your acetate or your polythene bars. But it's literally you're rubbing. And what you're doing there is you are ripping negative charges off the insulating atoms. So if you go back to our picture of the atom, what rubbing does is it enables the negative charges to be ripped off your object. Now, some materials charge positively and some charge negatively. So what we've got here is a rod, a material, which has been charged negatively. What's happened here is as this person has rubbed the rod with the cloth, then the cloth has lost negative charges to the rod. The rod has literally pulled negative charges onto it. So what happens is that you now have a situation where this rod is negatively charged and you have a cloth which is positively charged. Now, why is the cloth positively charged? Has it gained positive charges? No, it has not. It's lost negative charges. So the overall balance is now in favor of the positive. Now, because we have a positive charge here and a negative charge here, these would attract slightly. Now, this situation, it demonstrates charging by induction, which is slightly different. This happens when you bring a charged object near a neutral one. Now, seconds ago, this object here was neutral. It has the same number of positives as it does negatives, but what normally happens is they are evenly distributed. The negative charges are free to move, not flow. They're not leaving the sphere, but they are free to readjust themselves within the sphere. So by bringing this glass rod, which is positively charged, what it's doing is it's attracting all the negative charges towards one side, this negative side, this side which is now negative. Now, because the negative charges have vacated this area, this leaves an overall positive charge on this side. The consequence of this is that these two will attract each other. Now, this poor cat has been stroked vigorously, which means that it's probably accumulated a positive charge, and then the polystyrene bits it's been put in have had their charges redistributed, right? So all the negatives have gone close. If the cat, we're assuming, is positively charged, then what's happened here is all the negative charges have kind of like moved towards the cat. And so there is an attraction, and the poor cat finds itself surrounded by these annoying things. I wouldn't recommend you do this at home by any means, especially if your cat's got an attitude. Another quick example, which doesn't involve infuriating your pets, is to take a ruler, rub it furiously. Most rulers are made of acetate or some plastic. As you rub it furiously, what you're doing is you're charging it either positively or negatively, and then you break up lots of pieces of paper. Now, your pieces of paper will have a charge which can readjust itself. So if your ruler is all positive, then your pieces of paper will readjust yourself. So the negatives will go this way, the positives will go here, and it will fly up and stick to the ruler. And then the next piece of paper will do the same. It will adjust its charges in such a way that we get an attraction, and then an attraction here, and so forth. Lightning is another amazing example of static electricity at work, where you get an accumulation of charge in the clouds. Now, what's happening here is that due to convection currents force the hot air to rise and the cold air to drop. So you'll probably have clouds, layers of air which are at different temperatures, and so they move around in some kind of a circuit. Now, as they do that, they actually rip charges away from each other, and in such a way that your cloud will end up accumulating negative charge. So when we have lightning, we have an accumulation of negative charges. Now, eventually, because negative and negative, they repel, the charge needs to get away from each other. So, although air is not normally a conducting material, it does have some conducting properties within it, but minimal. But it will, basically, these negatives need to get away from each other so furiously that they will leap across. Now, when negative charges move in this way, that's called current. That's called a flow of charge, right? And that's what lightning is. These electrons have accumulated, are repelling, and they need to get away. So what they do is they discharge, they form a route to get rid of all those negative charges down to the earth. Now, I'm going to end today's lesson talking about the quantity that we use to measure charge. Now, charge is simply that an object is plus or minus. And so we need to measure how plus and how minus it is. And we use the quantity, charge, and the unit it's measured in, which is in coulombs, right? The symbol for charge is Q. I've added it in there, charge, Q. And the units, coulombs, are in capital C. Now, a whole coulomb of electric charge is actually a huge amount of charge. So therefore, we tend to, when we're doing numerical questions, use microcoulombs. To remind you, micro is times 10 to the minus 6 coulombs, or nanocoulombs, which are 1 times 10 to the minus 9 coulombs. These are more adequate measures for the kinds of experiments we're doing. But when we talk about a coulomb of charge, we're talking about a certain amount of negative charge. Now, a proton and an electron, which are the most common electric charges, have the same charge. They have the same amount of coulombs. And this is a really important number. So important that it is in the physics data booklet that you get with your exams. But all protons and electrons have a charge of 1.6 times 10 to the minus 19 coulombs. And this is a number that you always have available for you, but it's really important. It's important for this topic, and it's important for topic 6, and it's for a whole bunch of things. Okay, so please remember, what is the charge in an electron? 1.6 times 10 to the minus 19. So just to sum up, charge is something that can flow. It can move through a material. But when it's moving through a material, we'll call that electric current. And it can stay still. And when it stays still and accumulates, then what we call that static electricity. We call that a charge that doesn't move. So remember, insulators will be associated with static electricity, and conductors, which we're going on to in the next section, 5.2, are materials that do flow. And that's it for today.